So problem number 5 says an ideal solution having 0.3 moles of A is in equilibrium with its vapor having 0.6 moles of A. Calculate the ratio of pure vapor pressure of A and B, A to B. So here in this solution we have component both A and B. So we start to show the given is the mole fraction of or the number of moles of A, okay, is Na is 0.3. So number of moles of B if we say Nb, and if we consider total number of moles is 1, considering total number of moles equals to 1, so Nb will be 0.7, right? So Na, so since total number of moles, that is N here, so N is 1 here, so number of moles will be the mole fraction. Okay, so mole fraction basically. So mole fraction of A, therefore the mole fraction of A we call Xa is 0.3 by total number of moles 1, so we get 0.3, and the mole fraction of B so if we call it Xb is Nb by N, so gives you 0.7. Okay, so Xa vapor, so Xa vapor is says again Xa is means mole fraction of A in the vapor phase. Xa vapor if we say is 0.6, right? So Xb vapor will be 1 minus 0.6, so gives 0.4. Okay. Now we know Xa vapor is partial pressure of A in the vapor phase by P, total pressure. Okay. So we write Pa by total pressure is Pa plus Pb, partial pressure of component A plus partial pressure of component B. So we can write this one as 0.3 times Pa naught. Pa naught is the vapor pressure of component A for pure component A. Okay, and this is your 0.3 times Pa naught plus 0.7 times Pb naught. Similarly, Xb vapor will be Pb by P. So we get 0.7 times Pb naught by 0.3 Pa naught plus 0.7 Pb naught. Okay. So if we take the ratio, so we get Xa vapor by Xb vapor so we get 0.6 by 0.4, right? So this is given. So because Xa vapor by Xb vapor we also know. So Xb vapor is 0.4 and Xa vapor is Xa vapor is 0.6. So the ratio is 0.6 by 0.4. And so we can write this one as 0.3 Pa naught by 0.7 times Pb naught. So we need to calculate the ratio of pure vapor pressure. So we have to calculate Pa naught by Pb naught. So Pa naught by Pb naught will be 0.6 times 0.7 by 0.3 times 0.4. So we get 1.4 by 0.4. So basically we are getting here 7 is to 2. Yes, 7 is to 2. Next, we move to another problem, problem number 6. It says, a mixture of immiscible liquids A and B is distilled under equilibrium at 1 atmospheric pressure. It has ideal gas behavior. Calculate the mole fraction of A in the distillate if the vapor pressure of B is 425 torr. Okay. So there exists a unique temperature T at which distillation occurs. It is determined by the equation PA naught at temperature T plus PB naught at temperature T is 1 atmosphere. Okay. So for distillation this has to be there, so total vapor pressure has to be 1 atmosphere. Since the liquids are not miscible, because it says the immiscible liquid, so since the liquids A and B are not miscible, Raoult's law will be applicable each phase separately, right? Okay. So PA will be PA naught times XA, where XA is the mole fraction of component A, and PB naught times XB gives PB. So we can write PA plus PB equals to 1 atmospheric pressure, right? So we get PA naught plus PB naught, right? So since value of PB naught is given, PB naught is 425 torr, so PA naught will be 760 minus 425 gives you 335 torr. Okay. So XA vapor will be PA by P, so you get 335 by 760, so you get 0.441. Next we move to problem number 7. It says, in a bromine tetrachloride system, the mole fraction of bromine is 0.025 and its partial pressure is 10.25 torr. If the vapor pressure of pure bromine is at that same temperature is 213 torr, what is the activity of bromine in the solution? Okay, so here we know Pi, partial pressure of ith component, which is Pi is Ai times Pi naught. So Pa is AA Pa naught, okay, and so AA, because you have to calculate activity of bromine, so AA is Pa by Pa naught. So here AA is the activity of bromine here. In solution. It is given, so 10.25 by 215. So we get 0.047. So this is the answer. Next we move to problem number 9. It says consider the Henry's constant K for Henry's law of H2 gas in water is 5.34 times 10 to the 7 torr. Calculate the solubility of gas in water at 25 degree Celsius if the partial pressure of the solution is 760 torr. Assume the density of the solution is the same as the density of the solvent. So here X2 we know, X2 is N2 by N1 plus N2. So when N2 is very small compared to N1, we write N2, X2 is N2 by N1. Okay. Now number of moles in 1 liter of water, if we say this is N1, is 1000 gram by 18 gram per mole inverse. So we get 55.5 moles. Okay, so and for so X2, therefore X2 is N2 by 55.5, right? So P2 is K times X2. This is Henry's law, according to Henry's law. And K is 5.34 times 10 to the 7 equals to P2 by X2. So we write 760 by N2 by 55.5. So we get 5.34 times 10 to the 7 is 760 times 55.5 by N2. So from there we can calculate N2. So N2 is 760 into 55.5 by 5.34 times 10 to the 7. So we get 8 times 10 to the minus 4. So the solubility of H2 in water is 8 times 10 to the minus 4 moles per liter. Next we move to problem number 10. It says consider the constant K for Henry's constant of O2 gas in water is 3.3 times 10 to the 7 torr and N2 gas is 6.51 times 10 to the 7 torr. Calculate the ratio of the mole fraction of O2 to N2 in water at 298 K. So this is very similar to the previous problem. So we know P2 is K times X2, right? This is Henry's law. Now Kn2 is given. Kn2 is 6.51 times 10 to the 7 torr and KO2 is also given 3.30 times 10 to the 7 torr. So these are the Henry's constant for nitrogen and Henry's constant for nitrogen and Henry's constant for oxygen. Okay. So PO2 will be KO2 times XO2, right, and PN2 will be KN2 times X. So by definition, partial pressure equals to mole fraction times total pressure. So for ith component, Pi is xi, mole fraction, if we consider xi, mole fraction of ith component xi, and the total pressure is P. So Pi is xi times P, right? That we know. Okay, so partial pressure PO2 of oxygen, PO2 is XO2 times P, and PN2, partial pressure of nitrogen, PN2 is XN2 times P, right. So here we can consider this is Y here instead of X, because X already we considered, so we can consider Y here. So as I said, so YO2 is the mole fraction of O2 and YN2 is the mole fraction of N2, and P is the total pressure. Therefore, YO2 times P by YN2 times P gives KO2 times XO2 by KN2 times XN2. In atmosphere, O2 and N2 are present in 0.21 by 0.79 equals 0.27 ratio, right. So XO2 by XN2, okay, so will be your 6.51 times 10 to the 7 times 0.21 by 3.30 times 10 to the 7 times 0.79. So we get value is 0.52. So this value we have got, okay, and KO2 and KN2 are given, okay. So if we substitute everything there, we get, okay, so we get value of YO2 and YN2, right. Okay. Next we move to problem number 11. It says 0.4 gram of a non-volatile solute of molar mass 60 gram per mole is added to 100 gram of ethyl acetate at 25 degrees Celsius. After addition, what will be the vapor pressure of the new solution? The vapor pressure of pure acetyl acetate is 73 torr. Okay. So we know lowering of vapor, we know the relative lowering of vapor pressure P1 naught minus P1 by P1 naught, that is relative loading of vapor pressure, is W2 M1 by W1 M2, where W2 is the weight of solute to M2, W1 is the weight of solvent M, solvent 1, and M2 is the molar mass of solute 2, and M1 is the molar mass of solute 1, solvent 1. So this quantity, whole thing, gives relative lowering of vapor pressure of solvent, right? Okay, so without solvent, P1 naught was the vapor pressure. Without solute, P1 naught was the vapor pressure, and P1 is the in presence of solute. So that gives the lowering of vapor pressure. The numerator gives the lowering of vapor pressure, and if we divide it by P1 naught, we get relative lowering of vapor pressure. Now we substitute everything. So for the pure ethyl acetate, so this P1 naught here is, so P1 naught is 73 torr, right? Okay, and W2, because solute is 0.4 gram, and M2 is 60 gram per mole. W1 is also given. W1 is 100 gram, and M1, so molar mass of ethyl acetate, right? So M1 is ethyl acetate, the molar mass is 78, okay, gram per mole. So P1 naught is given, and W2, M2, W1, M1 all are given. So we need to calculate P1. Now we substitute everything. So 73 minus P1 by 73, and the value of W2 is 0.4. W1 is M1 is 100, and W1 is 100, and M2 is 60. Oh, sorry, this M1 is 78, not 100. M1 is 78. Okay, so if we further carry out this one, we get P1. P1 is 72 torr. Next, we move to problem number 12, which says 1.2 gram of a non-volatile solute of unknown molar mass is added to 100 gram of acetate at 25 degrees Celsius. After addition, the vapor pressure of the new solution was 183 torr. The vapor pressure of pure acetone at 25 degrees is 185 torr. Find the molar mass of the solute used. So here weight of the solute, weight of the non-volatile solute, W2 is 1.2 gram. Weight of the solvent, W1 is 100 gram. Molar mass of the solute we need to calculate. If we say this is M2, we need to calculate, and molar mass of the solvent M1 is 154. What is the molar mass of the solvent? No, solvent is 58 we are considering here. 58, okay, gram per mole. And what else is given here? The vapor pressure of pure acetone is given. Okay, so the vapor pressure of pure acetone, this is not acetate, this is acetone. So with the vapor pressure of pure acetone is given at vapor pressure of pure acetone, if we say this is P1 naught, is 185 torr, and vapor pressure of the solution is also given so vapor pressure of the solution P1 is 183 torr. Now we know the relative lowering of vapor pressure is P1 naught minus P1 by P1 naught. This is relative lowering of vapor pressure we just discussed in the previous solution. P1 naught minus P1 by P1 naught is W2 times M1 by W1 times M2. Now we substitute all the values. So P1 naught is 185, P1 is 183, and P1 naught again is 185, is W2, the value of W2 is 1.2, M1 is 58, and W1 is 100 times M2. So you get M2 is 1.2 times 58 times 185 by 100 times 2. Okay, so if we do it, we get M2 is 51.5 gram per mole. So this is the molar mass of the solute. Therefore, the molar mass of the solute added is 51.5 gram per mole.